morning, everyone. I am going to tell you a little bit about airtightness, what it is, and why do we need it. So a little bit about me. My name is Jüri. I have more than 10 years of experience in wooden construction industry. Most of that time I worked in a modular company, building wooden modules. Today I am a technical consultant in a company called Tervemaja, which in translation means healthy building or healthy house. So that's why it's actually important. It's the same sentence you already read, because in Tervemaja we believe that it is possible to build healthy buildings, ecologically healthy buildings, environmentally healthy buildings, and we can do that with conscious planning, and we need to have specific materials for that are also healthy. In order to achieve that, Tervemaja is representing several companies here in Estonia. One of the biggest ones is ProClima. Who doesn't know, then ProClima is a company that is mainly focusing on producing and developing airtightness materials. For example, vapor barriers, wind barriers. They also produce all kinds of tapes in order to seal it, grommets, and so on. We're also representing other companies like Fermacell, St. James Hardy, Styco, Multipor, and so on. So, plan for today. Very briefly, I'm going to talk about what airtightness is. After that, we can see why do we need it at all. And last but not least, we're going to see how to achieve it. So, I believe that many of you have been in a situation where a friend of yours calls you that, hey man, you know, I found this really great building, I want to buy it, but can you come and do the pre-purchase inspection or something? Well, I was in a similar situation a couple of months ago. I went to the site, there was this really nice building, it's all white, it has a nice roof, lot of insulation, it looked like really good. And when we saw the electricity bill, the house was heated with electricity, then I figured that something was very wrong, because the heating bill was way higher per square meter than my own. It was like 3 times higher. And when we started to look into it, where does it come from? Then we noticed that the whole roof, yes, it had vapor barrier there or air barrier, but it didn't have a single tape there. All the perimeter of the building was open, all the connections were open, even the air barrier was even disconnected from every single wall. So that was the main issue there. There was huge air leakage. So in overall, what the airtightness is nothing else than just the elimination of uncontrolled air leakages, both infiltration and exfiltration. Of course, in order to achieve that eliminated air leakage, you need to have air barriers on both sides. You need to make sure that your insulation is well encapsulated, so that it doesn't have any air moving inside it. Of course, it doesn't mean that we can live in a sealed box. Sealed box is going to be another big issue, so we really need to have some kind of ventilation there. There is this nice saying, build tight, ventilate right. So, in order to have some kind of ventilation, there are several different ways. A few of them are here. One of them can be that you just use a demand control ventilation. You can either manually turn it on and off from a switch. You can have a sensor that is checking your humidity levels in your rooms. You can have a sensor that is checking your CO2 levels, and they can automatically be turned on. You can also have decentralized systems. These are these little ventilation units that are inside the wall. They already have some kind of heat recovery system. They are automatically controlled. They can both pull the air in and push it out, so they can make some kind of air change there. Then of course we have the centralized systems, which basically similar to the one we have here, lot of pipes. Somewhere we have this huge machine, and these ones are really good because of the heat recovery. So all the air that you're pushing out of the building, you can use the heat from that to preheat the air you're getting back into the building. Last but not least is natural ventilation. That basically means that you open a door, you open a window, or you have these ventilation holes inside your wall. It's not very efficient, there's no heat recovery, but it still actually works. So what is the importance of ventilation? Basically, thanks to the ventilation, we are able to control the amount of fresh air supply that's coming into the building. Without it, we have uncontrolled air leakages, with that we cannot control at all. Thanks to the ventilation, we can control the humidity levels in rooms. We can make sure that it will be somewhere around 40 to 60% if we want to have a comfortable climate inside. And of course, some ventilation units can give us energy recovery systems, so they will be more efficient. So why do we need airtightness? Well, in reality, we spend most of our time inside. At the moment, we're inside, and it's around 90%. So it means that we need to have a comfortable place to be. What the comfort is coming from different aspects. We want to have stable room temperature everywhere. You don't want your one corner to be extremely cold, other one too hot. You don't want to have too high or too low air humidity. You don't want to have some draft or wind blowing through your hair like mine. So, yeah, you want to have a comfortable place to be. The other reason, of course, is structural safety. Structural safety could be one of the most important ones because we all know that we want the building to last 100 years, maybe 200. So in order to do that, we need to have some kind of structural safety there. Air quality, that's basically, thanks to the ventilation systems, we have filters, we can filter out the particles, dust particles from the external air before we push it back inside. So we can reduce the health issues, because the dust can be a problematic, especially for asthmatic people, for example. And the last one is money. I guess money is quite straightforward. We don't want to spend too much money in heating our buildings. And more about money. There was this really interesting test that was done in Ireland, I think. They built a real house, that was a passive house. They had the average element U value of 0.1. When it was finished, they made a blower door test. And the value for the blower door test was around 0.4, if I remember correctly. So it was as a passive house, has to be. And now they started to see what happened when they increased the air leakage in that building. And that's what the graph is actually showing. In the bottom side, you can see the increasing air leakage value. And in the vertical or left side, you can see the amount of euros that they had to spend in a year to heat up the building. In the very beginning, the money that they spent on heating was only 328 euros and some cents in a year to keep this house warm. And when they modeled it so that they increased the air leakage, then basically that's what you see there. If your air leakage is around 3, you will have around 3 times higher cost for heating up your building. So it's quite straightly connected with each other. The higher the air leakage, the higher the cost. Because insulation, well, we know that insulation is important, but all the insulation producers are giving these lambda values that only work if it's in a contained box or contained place where it's covered with vapor barrier, it's covered with wind barrier, and there's no air movement inside. Otherwise, these numbers don't work anyway. So testing airtightness, usually they are using blower door tests, some thermal cameras at the same time, and so on. They are testing 2 different ways, Q50 and N50. In Q50 they are measuring how many cubic meters of leakage per square meter of building envelope per hour at a differential of 50 pascals is leaking, and in N50 they are measuring how many times the old air inside the building is changing. The N50 is usually used for passive houses, so it's really important to know what you're talking about. If someone is talking about the air leakage, then there are 2 different values. They can be similar in some cases, but they are not the same. You can't compare Q50 results to N50 results. So just to put things into perspective, if you build a passive house, then the amount of air leakages, total amount of air leakages in your building is about the size of a credit card. All these caps and holes that you have there, it's no bigger than a credit card. But for a standard building, where you haven't really put too much effort into airtightness, the amount of, or the area of air leakages is around the ATM machine. So basically it would mean that you have a hole in the wall, about that size, and you never cover it. You never cover it, even during the winter time, it's still open. It's just air is moving in and out. So in very general, how insulation works, usually the heat energy is trying to move from warmer side to the colder side. For heat transfer, there are mostly 3 different ways. Conduction. This one is from molecule to molecule or atom to atom, so it's happening in solid materials. We have radiation, like sunlight. It doesn't heat up the space in between, but it will heat up the final surface where it's landing. And we have convection. Convection is the most important part for airtightness, as we're speaking here. So once again, in order to have insulation that works, we need to have this air in the insulation. We need to have it. We need to have air gaps there so that it won't be able to move. We need to restrict the air movement there. So with convective heat loss, there are usually 2 ways: open loop and closed loop convective heat loss. Open loop convective heat loss means that you do not have intact vapor barrier or intact wind barrier, so that the internal air can come from the inside, go to the outside, and during that process it's transporting humidity inside the insulation. It's also cooling down the insulation layer itself, which in the end will cool down the building, so it's not working really well. The second one is closed loop. It happens when, even though you have maybe sealed it really nice and tight, you have a vapor barrier, you have your wind barrier, but you have too much free air inside that layer. So you will have internal circulation of air, which will also start to cool down the insulation layer. And once you cool down the insulation layer, you will cool down your building as well. So here is one example of open loop bypass. In the left one, you can see the picture that was done before the blower door test. And on the right side, you can see what happens when you start to depressurize the building. In that case, it's pulling cold air from the outside to the inside because of the low pressure in the building. And you can really easily see that the whole insulation is going green or even blue, so it's cooling down. And in the same way, it's cooling down your building. And actually, they made a test about that as well. It was done quite some time ago by an Institute of Building Physics in Stuttgart. They took this 1 meter x 1 meter element, around 140 millimeters thick. They filled it with mineral wool. From one side, they covered it with vapor barrier, from the other side with wind barrier. So they had this perfect element, no air leakages. Now they put it into climate chamber. And they tested 2 things, U value and how much vapor or humidity is getting inside that element. Well, the U value was basically something you would get when you calculate it, around 0.3. And the amount of vapor or amount of humidity that got inside that element during 24 hours was just 0.5 grams, which is extremely low. But what about the test in not so perfect conditions? They used the same element, but now what they did was that they sliced it in the middle. So now they have a 1 millimeter cap in that element. Everything else is the same. They put it back into the climate chamber, and they tested the same things. They tested U value and how much vapor or humidity is getting inside that element. Well, U value dropped from 0.3 to 1.44. The total reduction factor was 4.8 times. So even though you might have quite thick insulation layer, it doesn't give you the effect you want unless it's sealed correctly. And the other crazy part was that the amount of humidity that got inside that element was not 0.5 grams anymore, but it was 800 grams. So a total of 1,600 times higher than before. Maybe many of you have heard that sentence that this cap, one cap does not change anything, or you don't have to tape it, you don't need that, it's just small leakage. Yes, usually nothing happens. It usually takes more than one thing to go wrong in order to have structural damages. But with wrong materials, it can quite easily happen, as you can see in these pictures. All of these things had an issue with the vapor barrier and the upper layers that weren't also releasing any humidity anymore. But what are materials from airtightness perspective that are actually good? Well, the best solution for sure is using special materials, for example, vapor barriers, wind barriers. They can be both fabric or they can be boards, it doesn't really matter. These things are made for that, so we know that they will last there, and that we know that works. Of course, glass is extremely airtight, but I believe none of you is going to use glass as a vapor barrier, but it's also good to know that the glass facades that we have, the windows that we have, that through the glass nothing is really leaking. Of course, there are the connections around the window and so on, but the glass itself is really airtight. The third one is wood, or in this case CLT. I think Kevin is talking more about log specifically in the next presentation. But in overall, CLT or wood is actually quite airtight as well, so it is possible to use that as airtight material too. The fourth picture, it's meant to be a plaster or render, and it's put on a stone wall or a brick wall, because even though these thick stone walls and brick walls, they look airtight, but if you pressurize the building or depressurize it, there will be air leakages, and actually quite high air leakages. So it is really important to use correct plasters or renders in both sides of the stone block or brick wall to have the best possible outcome. There are also some materials that are not too airtight. Basically, using any other tape that is not meant to be airtight material, you should not use it. They usually don't last there. So it's really important that you use specifically airtight tapes. OSB, which is actually really good material, but standard OSB is not airtight. I don't know how well you see it or not, but in the top part, they are taping a plastic foil on top of the OSB board, and now they are pressurizing the building. And in the bottom part of the building, you can see how that plastic is acting like a bubble now, because air is leaking through OSB into the bubble there. Of course, there are actually OSBs that are specifically made to be airtight. They are also laminated OSBs and so on that are airtight materials. But in that case, a standard OSB is not to be considered as airtight material. It's very good for different other things, of course. The third picture actually shows kind of the same thing, but through the stone block wall. Once again, it's not airtight, it needs to be plastered in order to have best possible outcome. And the last one is different kinds of silicons that are not specifically made for airtightness. Standard silicons usually tend to crack in a few years, maybe even less. So even though you might, thanks to the silicon, you might actually maybe pass some kind of blower door test if you do it right away. But after a few years, you will have air leakages for sure. Of course, there are special materials, special hermetics that are made for that. But once again, as with tapes, you need to make sure that you get the correct one. And then there are just some things that are not too good ideas. Foam itself, in some places, is actually a really good material. But excessive use of foam definitely means that something actually went really wrong there. So they're just trying to fix something that shouldn't be fixed like that. And the last two pictures are showing two cable penetrations. One of them is taped with something, but taped wrong because the connections still are not airtight. A lot of vapor got under the roof. And the last one just shows that there's absolutely no taping at all, or grommets. But how to achieve airtightness then? Well, as with any other problem in a building, the best way to start with it is during the construction, but the designing phase. You need to understand where you want to have your air barrier layer. While doing that, you can define the most critical points. You which will probably be the connection between floor elements, wall elements, windows, all kinds of utility holes, penetrations, and you really need to work on these details. And during the detailing, you also need to make sure that you use correct materials. For example, in ProClima homepage, you can find very many different solutions that are already designed very well. Here you can find what materials to use, where to use them, how to use them. So they will help you a lot already how to achieve the best possible airtightness. For example, in the left picture, it's actually quite a common problem with airtightness. Even when you finish your airtightness layer, you do it very well. Then electricity sockets might be going through that, so you're really ruining it once again. But even for that, there are actually specific materials that you can put behind there, or you can either use the standard solution to have an extra pattern inside and just put all your cables and sockets in between the air or wool layer, so without penetrating the air barrier. And the last one, of course, windows, doors, where to put tapes, which tapes to use there, and how to make it airtight. Here are some really good real-life examples. You can see that already during the construction or assembly phase, they are installing part of the vapor barriers, because if you would like to do it later, then you can't really do it correctly anymore. Because in that case, you know for sure that you have your vapor barrier behind these elements as well. So that's really good example of a pre-thinking or pre-planning. Yeah, here are a couple more. The left picture is actually a two-story building. In here you can see that the first floor has been already assembled, basically. The blue fabric that you see here, this is actually air barrier that will go around the floor elements, so that you can connect the first floor and second floor air barriers with each other around the floor element. So this is once again a really good example of how to do it correctly, so you can make sure that you don't have any constructional air leakages inside the elements later on. And the right one shows how to do, for example, in any brick wall or any stone block wall, how to do the sockets. If you want to avoid air leakages, you need to either use plaster, as you can see here, you have to plaster it from the behind. Or today, actually, there are also liquid membranes that you can just spray on or crush it on and make it airtight. Yes, and airtightness is a combination of very many different people. It's not that you have one person that is dealing with it, because we have HVAC guys, we have ventilation guys, we have electricians, general builders, we have everyone on the site. So if you want to make sure that everyone knows what they're doing, you have to make sure that your people know what is airtightness and why do we need it as well. Because otherwise they don't really understand the problems they are causing. If possible, do the blower door test after you have installed your airtightness layer, because in that case, if you have any leakages, any problems, you can fix them quite cheaply. And of course, if possible, let your workers see that as well, because if the workers see themselves where they have messed up or where they have done well, then next time they will be even more, they will be more happy to do it, they will know what to do and how to do it. So it's going to help a lot if people know what they're actually doing and what the air test really is, or blower door test. So, conclusion. So, I would say that airtightness, according to everything I already said, airtightness is important, mostly because the main thing is money, because we all know that we don't like to pay too much money. Of course, the air quality issues, comfort, it's all important. Which is maybe even more important is that there are a lot of ways to achieve it actually. There are different materials, different technical solutions. We just need to look into it a little bit, if possible, do the planning as soon as possible. Then it's easier. You don't have to really figure out something too complicated. Last but not least is that everyone can do it. You don't need to have this special airtightness guy on your site to have airtight building. You just need to make sure that your people know what they're doing. And that's how we get airtight buildings. That's it from me. So, thank you. really heard about the foam that is natural or something, but for example, in windows you can use stone wool, glass wool, or wooden fiber wool or whatever, because either way, if you're going to tape it correctly, then you just need to have some kind of insulation there. It doesn't have to be foam. Foam is one solution, but foam itself is not airtight material once again, because even though there are foams already that in laboratory are tested as airtight, but the connection between the original element and window and the foam, this one is not tested yet. So there could be a crack in a few years, maybe as with silicon. And if you have a small crack there, it's going to be a air leakage, unless you have correct tapes both sides of the window. That's going to solve it. In that case, the foam will work there, even though it's this micro cap.
So you've seen, from your testing, you've seen foam fail for air sealing?
In blower door test, it has been shown that they will leak, yes, eventually, if it's not taped. If it's taped, then it's all good. Of course, there are in different markets, different products. Maybe somewhere you have a lot better products already. I'm not sure about that. Maybe, but yeah, air, I would say you need to take it anyway.
20 years ago, you had foam made of soybeans, but I'm quite sure that it's not.
Yeah, there's still some foams that are soil-based, but with the log home restoration, where there wasn't gas being used, it's hard to, your only option is to inject spray foam into the corners.
Mm-hmm.
And it's like, that's what we've been doing, and it's you can't really pack wool in.
It's still better than nothing,
Yes,
because you will fill the big cavity, you will have like this cavity there.
Yeah.
It doesn't mean it's 100% airtight, but it's a lot better. As you saw from the graph, every single thing that you can close is going to help you. It's going to reduce the heating cost.
Yeah.
It doesn't have to be perfect, but it has to be as good as possible. Actually, I have heard about I had this training where they had a building, a new passive house. When I said that passive house had a 0.4 air leakage value, then now they made a passive house with an air leakage value of 0.047, so almost 10 times smaller than the one in that example. And if that example, the total area of air leakages was around credit card, then in the next building that they had, it's like the size of a thumbprint. It's really, really small. So it is possible, but of course it takes a lot of work, a lot of planning, and yeah, but in the end it's going to be a lot cheaper to have this building.
Anybody have any more questions? The next speaker. I'm going to be the next speaker. Hello? There we go. And I'm going to be, I think most of you everybody was here yesterday? Okay. So most of you know my bio then. Just going to bring up my slides.
Just push it forward.
Okay.
Yeah.
I'm going to be talking about inspecting log homes and finding some of the water issues, because what happens is when we start building these buildings over 4 or 5 years after the log homes start to settle, then they start finding issues and problems with these homes. As we know, that log buildings typically take 4 to 5 years to settle. So what we find out is after they've been tested and after blower doors have been used and finding the problems and issues, they still can happen and come back. But as what I've been focusing now is primarily restoration. I do home inspections and litigation work. So some of the things that we do is we're correcting problems of the homes that builders can't find. This is my lovely wife. I think you guys saw her in one of the other slides, but this is during the COVID years. I tried growing a beard, so we try to change it up a bit. And obviously my wife doesn't like it, so it's gone. Thank goodness COVID's over. So this is a house that was built. It was a log home, and a new roof was just put on, and they thought there was going to be, it's going to solve the air sealing and airtightness issues of the log structure. But this was a complete disaster. So what we use is we use the blower door. This is a great piece of equipment if you don't have one already. It's becoming more and more popular. That when I was in Estonia, 2010, this is what I talked about as blower door testing. We did a lot of blower door testing on log structures and finding out where the air leakage is and where the pinpoint problems are. Because a lot of builders were scratching their head, hey, where is this water coming into the building? You know, it's like you don't know what's going on. This blower door makes a big difference in finding air leakage and water problems coming into the building. Because as Jüri's talking about, you got a stack effect. Hot air rises. Every cubic foot of air that leaves the building, another cubic foot of air comes into the building. So if we have a strong wind gust, it can actually pull a vacuum on the building. So if your caulks or sealants have failed, you're going to find these areas where normally just running a garden hose on the building and doing water testing, this is going to speed up the process and find out where that air leakage is or where that water is coming into the building. And on log structures, we've actually found water coming in through knot holes. So it's like an actual knot on the side of the log can be a potential problem on a building. So it's just because you build a new building, you could be scratching your head. It's like, hey, where is this water coming in? Because it's like the homeowner just built a brand new home, and now where is that water coming in? So it's like you got to really think outside the box of where that water is coming in. So it's like it could be a knot hole, it could be a check or a crack in the log. So if you've got problems and you need to solve them fast, this is the tool to have. Going back to that house, all the blue tape is where we found air leakage into that building, and they just basically used fiberglass and a vapor barrier, but it's going to be really difficult to air seal this building off with the problems they had. Because as we're building these houses tighter and tighter, it's like driving a race car. It amplifies the problem. So making a building energy efficient, the best way, the cheapest way of doing it is by air sealing it. But in retrospect, if it's not done correctly, you can amplify the problem of what's going to happen. As you can, it's hard to tell on the photo, but these are all moisture stains on the ceiling. So it's like, how do you correct that? It's like, okay, we either have to go in from the inside and spray foam it, or from the outside. And a new roof was just put on, so it's like, we don't want to really damage the wood on the inside. So basically, the conclusion was taking the roof off and doing it from the outside versus doing it from the inside. I didn't do the work on this, on the air sealing aspect of it, but we're just trying to come up with different solutions on different ways of doing it. And normally you could just pinpoint the areas where you could spray foam it in, but since this was such a mass area, it was easier to do it from the outside and just spray foam the whole upper deck and take off the roof sheathing, which is an expensive fix. Yeah, you can just see where the leakage is. I mean, imagine building your dream home, and now your workers didn't seal it off correctly. Now you're getting into lawsuits, litigation, you're getting into problems. It's like, this is what we're trying to avoid. So when you're starting to air seal a building, it's very important. It's like Jüri was saying, it's like, hey, we got to go through our crew step by step and make sure that it's done right. We need quality control. We need checks and balances, because otherwise, once this is enclosed up, it's very expensive to fix or retrofit. Up in the upper ceiling too, this is where we find a lot of the air leakage problems around the ridge pole and around the fireplace, because a lot of times there has to be clearance for combustibles, but they do make products now that are fire rated for air sealing. So a lot of times people think, hey, it's the roofer's problem. You know, they didn't flash the building correctly. So the roofer gets called in and they're looking at it and water's dripping down, and it's not a flashing issue. What's happening is that hot air is rising because of the air leakage, and now it's condensating, and that water starts dripping down. So a lot of times people think, hey, it's the roofer. No, we got an air leakage issue problem. So a lot of times it's not the roof. Just because you have water coming into the building doesn't mean it's a roof leak. A lot of times it can be an air leakage issue. So when you're trying to find water issues and water problems, could it be a roof leak? Yeah, but it also could be an air leakage issue. So you really got to put pen to paper when you're trying to figure out where these water issues are and where the water problems are. Then we had water coming into the side and the roof up here. You can see the photographs. So there was a log wall on the outside, and with the stack effect during certain wind conditions, the water was actually getting sucked right into the building. Can lights in the ceiling, that was another issue. How I look at it on a building, the newer lights that we're putting in are a lot better. They're airtight. But on these vaulted ceilings, again, the best way to explain it to your clients or your customers, picture your house as a hot air balloon. Hot air rises, but as soon as you put a bullet hole in that balloon, that's where you got air leakage, and then that's where you get condensation and moisture issues. So this is a bullet hole in your hot air balloon, and now when that moisture rises, you're getting condensation and it comes down. But the technology has increased dramatically over the years with these can lights to make them airtight, to have not problems. But sometimes at these older houses, you might run into this. Again, you know, quality control checks. It's like we have the vapor barrier there, but if it's not taped or sealed correctly, then you have that water condensating from the inside. And you can see all the staining that's going on. And this was in a knee wall area, but now how do we get to the vaulted ceiling area? That's going to be really hard to fix. And that's what we're trying to avoid. We don't want to get into problems or issues with our clients. We want to try to do it correctly and make sure it's airtight and done right. Otherwise, you can amplify the situation. Again, can lights. You know, these are, as we had the checklist of what needs to be done, it's like, okay, is it the electrician's fault? Is it the insulator's fault? Is it the builder's fault? The the general contractor's fault. It's like, no, you need to work together as a team and understand where the problem is and where the air leakage is coming. You got to bring it back down to basics. And that's like how I always explain, hot air balloon. People can relate all over the world with a hot air balloon. This goes back to the house. It's just like a new roof was put on. It's like, hey, what do? Now we got a $30,000, $40,000 roof. Now that's all got to be taken off, and now we got to air seal it and make it tight. Because a lot of the trades don't communicate with one another. I don't know if that's a problem here, but it's like, oh, it's the drywaller's fault, or it's the painter's fault, or it's the roofer's fault. It's like, or it's the electrical person's fault. It's like, hey, you need to communicate with all the trades. We need to work together as a team and being responsible with what's going on with these houses. That's part of the preservation aspect of it as well, is building it correctly. This is another house that we worked on. This one was a challenge. This was, maybe Rebecca, it's in Baraboo, but what would be the cubic meters? Otherwise I'd be talking square feet. It's huge. Let's put it that way. It's about 12,000 square foot house. It's a mansion. And this is, working on big houses like this was a challenge because the blower door that we used wasn't big enough to find out where some of the problems were. So we had to section off some of the houses or some of the rooms to be able to get enough draft to find out where some of the problems are. And you know, this guy, yeah, he's got money. But when you're building a dream home, whether it's a small home or a big home, and you're building something for somebody, you don't want to build something where you're getting called back on and having problems or issues. I mean, this is what gives our trade a bad name and a bad reputation. Is it's like, hey, log buildings are leaky, drafty, high maintenance. We're trying to prevent that. So water was coming in to the building through checks, but this one, we actually had to come back on this building. Like I said, this was a challenge. It's like, you don't know, you think you know what happened, what the problem is. And sometimes you figure it out, hey, this is what, okay, it's obvious. Flashing around the windows, maybe a check, wasn't sealed right, the flashing tape. That could be all the problems of this, right? But realistically, that was part of the problem. We did find a lot of our air leakage issues. We spray foamed the corners. We spray foamed the inside of the windows, and then we thought we fixed the problem. But guess what? That wasn't it. The windows failed as well. And we don't have as good as windows as you do, but back in the States, these are Marvin windows, and that company is considered top of the line for windows. So not only did we have air leakage issues with water coming in, but all the seams and the seals along the windows failed as well. So it's like you really got to think about what's going on. Just because you have a good window doesn't mean that can't be part of the problem. It's like things failed. Like I said, I do expert witness work. And we've had buildings where all of a sudden the concrete wasn't mixed correctly. Or, you know, there's a problem with the stains or sealants because on the caulk tubes there's batch numbers. So just because you bought a high-end caulk from Sansom or Sashko or Permachink or Rotoblast or any of the manufacturers even in the area here, we're humans. Stuff goes wrong. I mean, even cutting the lawn wrong. You know, it's like when you're finding water issues and water problems, don't think it's just one area. It could be a window problem, it could be a caulk failure. You gotta think outside of that box that, hey, maybe it was a bad batch. Again, I mean, this is a big home. We had to go up scaffolding in the inside. So to give a retrospect, it's like the inside of that great room was taller than the ceiling. So yeah, I don't know my metric system that well because we're still on an inferior system, but that's another subject. But it's like the cost involved, and it's like, I don't know about you, I'm not filthy rich, but when I go in this guy's house and I'm working on stuff and I know there's like a $30,000, $40,000 Persian rug that I'm working underneath, it's like I get a little nervous. Yeah, you can get an idea from the photographs on how big this house is. But what was surprising is all the windows in this building needed to get replaced. It was a manufacturer's defect on the windows. I would have never guessed that in a million years. It's like, oh, it's a Marvin window, top of the line windows. It's like buying a Porsche 911. Hey, I got a Porsche. Shouldn't be any problems with it. Even when you buy a Porsche, you can get a lemon. So just because you have top of the line doesn't mean you can't have problems. And yeah, that was over $170,000 worth of glass that needed to be repaired on this building. And they had, 6 or 8 different contractors in this building trying to find out what the problem was. And we're the ones that figured it out. They had roofers in there, they had general contractors in there, they had everybody and their brother in there that they could possibly think of. And we figured out what was causing the problem. And even the Marvin rep was kind of shocked that all the glass was bad. But stuff happens. You got to think about it. It's like, don't be in a single mindset on what the problems are. Thermal imaging cameras, great tools. These have come down in price dramatically. Now even FLIR even makes an attachment on your iPhone, you know, for a couple $100. The better cameras with the higher resolution are great for vaulted ceilings. If you're doing a lot of high work, then you need to spend the money to get a high resolution camera. But when you're running water in the building, you can find out exactly what's happening, what's going on really fast and efficiently. But again, this is the one house that threw us for the loop. It's like, okay, we fixed the water issue. We air sealed it, we airtight it, but it's still leaking. It was the windows. So just because you think you fixed the problem, there could be another problem that's also causing it that worked hand in hand. Hard to tell, but that was my wife out there. She had to help me run water on the building and communicate, you know, start low, work your way up. Stop, you got water coming in. So, but yeah, you just don't know where some of these problems are. You always got to think outside the box. Yeah, water's coming in the corners. So we had to spray foam and inject and foam in all the corners, keep the water from coming in. So with this one too, it was like we had water coming in the inside of the building, so we spray foamed all the corners, spray foamed all around the windows, figured we fixed it, but the doors and windows failed. So that was part of the problem as well coming into the building. Because when we did our water tests and our thermal imaging scans, like, hey, we got this. We fixed the problem. You know, oh no, we still got water leakage. Then what do? You know, scratching your head. So then we figured out it was the windows and the doors. This is another interesting house. This one is a proven fact of what the stack effect can do in the hot air balloon effect. So from this photo here, way up high on the window, I gotta zoom in on this, but look at the good overhang on here. I mean, it's got good protection, but the homeowner said, hey, during a west wind, I'm getting water into the building. And he can't believe that water's coming into the building up high because you got a good overhang. So what was happening? Well, again, house, hot air balloon, hot air rises. The same amount of air that leaves the building needs to come in from the building at another area. So with that west wind, it created the stack effect, and in this area, it actually created a vacuum. So with the stack effect in the hot air balloon, it's actually sucking that water right in. And like I said, I do home inspections as well. And if I was inspecting this house for a client, I would have never known that water was coming into the building. But in our states and our laws, the homeowner has to disclose if they have a problem. So if I would have missed this as an inspector, the homeowner would be responsible for this. I mean, what's amazing is it's probably hard to tell from this photograph, but there's only like a 1/16 of an inch gap. And this was under the overhang. Hardly anything. But that's where the water was coming in. I mean, during a west driving rain, he was getting about 4 liters of water into that building with that little crack. I mean, that's pretty... So when it comes to looking at a building or how important it is when sealing it tightly, it's like just that little detail is what caused all that water to come in. 4 liters of water under an overhang. And what happened was, like a lot of the trades, the caulk was great quality caulk, but it wasn't installed to manufacturer specifications. So when this failure happened, they didn't leave a big enough groove in here, so they just smeared the caulk on here, because a lot of the caulk manufacturers require at least 3 or 4 centimeters for that caulk to bind in, and they didn't leave that groove in here for that caulk, so it was an installation error that it failed. But it didn't fail in 5, it took about 15 years for that to fail. But if it was installed correctly, it wouldn't have failed at all. A little bit closer detail. You can just see, even under that overhang, that's where the water was coming in. So it's like when you're trying to figure out these areas, don't overlook a minute crack. I mean, a check, a knot, even the seals on the window, because it's like you think on the window the seals are all good, because you can't see it. But you only need a millimeter opening with the stack effect of a building to draw that water in. So if you ever have issues with buildings, you know, you really got to analyze it, and the blower door helps you out a lot. So you don't have one, find somebody that does have one if you can't figure out how the water's getting into the building. The other way of getting, if you don't have a blower door and you're trying to figure out water issues, if you close all the doors and windows in the building, run the dryer, run all the exhaust fans, and run the exhaust hood in the kitchen, you can create the same effect as a blower door. So if you're in a pinch and it's like, okay, I'm running my water, I can't find out where the problem is, run all the fans and run the dryer, run every fan on in the house, and you can create almost the same thing as doing a blower door test. So it's a cheap way of amplifying the situation on problems if you don't have the equipment. But thank you, appreciate it. If you guys got questions, you can always ask me. Our next speaker, Mikk Luht. Did I say that correctly? Not at all? I have problems with these European names. Sorry. Mikk Luht. Is that better? Luht. That's Norwegian. Complete Center for Ecological Building. They advise and content organizations, companies, and individuals operating in this field offer a wide range training, services, promotional, traditional, and modern solutions in the fields of energy, efficiency, construction, and natural building materials.
Thank you. So hello to everybody. My name is Mikk, representing Competent Center for Ecological Building. And as said, this organization advises and connects individuals, organizations, and enterprises that are active in the field of ecological building in Estonia. It also works kind of like an umbrella organization, especially for the bigger projects that are international or also local, where just private companies can not join, and it is expected for an umbrella organization. We offer a wide selection of trainings for different target groups, starting from kids in the kindergarten to professionals like architects, constructors, and so on, and everything between, university, schools, self-builders, and so on. We are part of different kind of networks and associations, like European Earth Building Network and European Straw Building Association, and we are a training partner for Estonian Unemployment Insurance Fund as well. Of course, our daily work is to promote natural building materials and energy efficiency construction. And we also initiate research and scientific researches and product development and so on. So in 2020 we opened a product development training and competence center in Moosta Maynard complex. Probably some of you have been there, or some of the participants also are accommodating there during this conference. So we are located in an old stable and garage house, which we renovated with the help of European funding and the local government, and with a lot of help of members of our organization. So we are focused on earth, lime, and natural fibers. We of course also use a lot of timber in our work, but we rather work more on a niche with earth and other natural fibers, because there's so many organizations, as also the Wood House Estonia, which is organizing this event, and handcrafts who are working with timber. There's no point for us to duplicate the work that they are doing already so well. So we have chosen a narrow niche. And there are so many other natural fibers. Timber is the most common, of course, especially in Estonia, where it has been one of the main construction materials more than 1,000 years. But there are so many other fibers as well, like flax and hemp, reed, straw, coconut fibers, bamboo, whatever. So among our members, there are material producers, architects, engineers, project managers, constructors, finishers, project managers, already said, trainers, so on. It's not a very big organization, but Estonia is also a small country, and natural building at the moment, unfortunately, is still a rather niche. I also have to apologize, I didn't consider that the screen will be so small, so there are some slides that have many photos on the same slide, so you can come closer if the visual part interests you. So, I will, although the subject of this conference is actually like revitalizing heritage, then I will talk rather in a modern aspect of ecological construction and finishing, although the materials are one of the oldest that humankind has been using. For example, earth. This is probably one of the oldest building material that mankind has been using, and definitely the oldest binder, as clay as a binder, like way older than lime or gypsum, or of course, we are not even talking about Portland cement, which is just from the last few centuries. And earth, you can use earth for bearing constructions. You can use it also for insulation materials, which is like a light earth, where you combine clay slip with either organic insulation additives or mineral additives, and of course finishing. So, why earth? This is really easily available material with a really small footprint, super environmentally friendly, very friendly material to work with for the crafts, and it's a forgiving material, and you can use it if you don't treat it thermally or chemically, which is not needed for this material. Then you can use it, reuse it endlessly, because you just have to add water to the material and you can mold it and give it another form again and again and again and again, which is not the same thing with other binder-based materials like gypsum or even lime, and also cement products. You can't treat them in the same way. And also, more and more nowadays, when we are looking to the future, in the first presentation this morning also was stated that in Europe now we will have new norms starting from 2028, that all the new buildings that are bigger than 2,000 square meter public buildings have to have also material label. Now, at the moment we have this energy label, but also the material label in the future. And from 2030, all new buildings have to have this material label. I mean, there will be probably also a lot of manipulating with terms and numbers as it went with the energy label, but it's a step forward anyway. Hopefully, something good comes out of it. So it also means that we have to really look what kind of materials we are using in the construction and for finishing as well. And also, Jüri was pointing out this in his presentation about the interior climate or indoor comfort. mentioning mainly of the humidity, temperatures, air quality, so on. There are actually many other aspects, but which also influencing the indoor climate and the quality of that. And materials are playing a big role in it. Not just the construction and the finishing materials, but also the textile, furniture, everything that is influencing the well-being of human beings in indoors. And when the new house is built, we dug a foundation. If it's not built on the post or screw foundation, then we probably dug some soil out. And if the soil consists some clay, then it's probably also usable for some other materials. At the moment, usually, this is considered as excavation waste. People are paying money and using energy to transport it away, and probably paying money for the places that are taking that as a waste, instead of using it on the same site to produce materials for construction or finishing. But this is also slightly changing. There are some pioneer projects also in the bigger cities, and I will scratch just the tip of the iceberg today. It's a short presentation. I just show some of the possibilities of using the material. So compressed earth block consists either clay, sand and gravel, or if it's already earth that is suitable, which has clay and then silt and then gravel inside, you can maybe use it directly. And it's up to you whether you want to stabilize it, either with organic or mineral stabilizers, to improve the strength, compressive strength and weather resistance. So the raw brick is produced either with manual or automatic presses. So these manual presses, drawings, I mean, you can find them everywhere in internet. If you're a self-builder and you want to build yourself one, you can easily find a guide how to build one yourself. Or, of course, you can go back and do it in even in an easier way and use some mold to produce mother of all bricks, adobe bricks, which is different kind of raw earth brick with more plastic state of earth. This mixture is really slightly humid, and the high pressure from the press is doing all the work. So you're compacting it with really powerful pressure. And these automatic presses are also available in a mobile way, so you can very easily bring the production on the certain building site, use the local earth, move on to the next one. So, I don't know how much to see. There's also probably the reflection. On the left corner, top left, is our own competence center in Maynard. These earth blocks are produced just a few hundred meters away by one of our members, company that produces raw earth materials and lime blasters and other natural building materials under the brand name Pure Earth. And we were using these for partition walls. Top center is a regional house in Belgium, where this house was actually built inside an old hangar, like this one, and local earth was used during the workshop. Participants were pressing the blocks and also helped to build it, and is insulated from outside with hempcrete, which is like a mixture of hemp fibers and lime. It's like insulation material. Top right is exhibition work we did last year with one of our members, a design studio called Juurikas. They are focused on earthen materials and techniques, and this clay was dug out from Tallinn, from the streets called Sõpruse puiestee. where our biggest construction and real estate development company Merko was starting to build a apartment house. And again, of course, this material was moved away, considered as a waste. We do some portion of that material and did a product development, developing a rammed earth mixture, compressing these compressed earth blocks, doing some base coat clay plasters, fine finish clay plasters, and clay paint. And an exhibition in VMC Atrium was organized just to raise awareness. But big things happening in Europe as well, like the top right bottom photo is a project called Cycle There, which was started by our good friends and colleagues in France. And when they started to prepare for the Olympic Games that are taking place this summer, they are excavating a lot of new, or they're widening the subway in Paris for that reason. And they are excavating like millions of cubic meters of earth. And they established a factory close to one of these excavation points, and they are producing blocks, boards, mortar, and other materials which are used right away in the same area in new real estate developments. So this is like a really project on a bigger scale, and showing how it's possible to use these techniques in bigger cities as well. And Town Right is another project in the Netherlands, where also a railway junction was built, and 60,000 compressed air blocks made on the site using the material that was excavated and used right away also there as a noise barrier. And oven builders are loving these blocks because it's really easy to shape if you want to have like a curvy form for your mass heater. So rammed earth, actually one of the oldest earth building techniques, but coming back because it's, it's labor intensive, but it has a really small footprint. It has very good benefits for the indoor climate, and aesthetic point of view, of course, is also important. Architects are loving it. So the technique is again, the mixture is slightly humid, and it's damp between the formwork in layers of 10 to 15 centimeters. Historically, of course, using manual dampers. Nowadays there are pneumatic dampers to do that. And there are companies already in Europe and also in States who are producing prefab panels out of rammed earth and these ore blocks, and they are put together later on the building site. Some samples. For example, on the top right, there's a Regal Herb Center factory facility, company that produces candy, herb candy. This one is built with these prefab rammed earth panels. Although the structure there is a steel beams, and the panels are put between the frame. The chapel in Berlin is top left. And down right, there's a huge conference hall in Wales, in Centre for Alternative Technologies, 7 meters high wall in a conference room. And you can also play with different colors of earth when doing the rammed earth. You can add different kind of mineral additives in decorative purposes to different lines, or depends how you prefer. You can also do it like a very rough. And not just for walls or floors, you can use it also for different kind of decorative elements or for furniture. There's some town left. Is a museum in France that was installed by our colleagues in France. Top left is a Estonian project where there was a TV show where restaurant was built with 7 days, and then the round wall was where they serve food for guests. So Bored Earth, this is something that is especially interesting when we look in the future, and a lot of work is going on here and also by our European partners. So this is basically the idea to do the concrete and not using Portland cement as a binder. The reason, of course, because there's a huge emissions related with the cement industry at the moment. So if the perfect way would be if they are collecting all the excessive heat that they are using and also collecting all the CO2 that is coming from the production. But yeah, so I mean, the clay concrete, so to say, or Bored Earth is not meant to build bridges or skyscrapers, but we can do floors, we can do partition walls. In warmer climates, you can also build exterior walls and so on. And it depends how you treat it or how you stabilize it with natural additives. You can also improve the weather resistance and the compressive strength and so on. So here's some examples of a kindergarten in the left in France, and there's a residential building in States. This is actually another technique called casted earth, which means that the earth is stabilized with gypsum. And of course, 3D printing is also a huge subject, not just in the construction business, but everywhere else. So, and as well, any other construction or any other area that we are looking, everybody are looking for possibilities to automate the processes and to develop more easier ways to build, quicker ways and so on. And natural building or ecological building is no different here. Everybody are looking for the prefab solutions, and 3D printing is also one way that things are moving. So it has been mainly tested with 2 different materials, like opposite materials, with concrete, Portland cement concrete, and the other way is to do it with earth. Leading company on the field doing it with earth is Tekla. It's an Italian company, and they are mixing earth and using rice husk and dry straw as a fiber in the mixtures. And of course, finishes with clay plasters, clay paints. This is also something that has going hand in hand with log building tradition in Estonia and also many other countries, because clay plaster is a really good way to finish log buildings, to protect them from fire, to improve your interior climate, and of course actually also to improve the airtightness. Obviously you can't achieve same result as you could do with membranes that Jüri was talking about here, and but still it improves that. So clay plasters can be used to finish walls, ceilings, floors, and the benefit of it is that you don't necessarily paint the plaster, You have different kind of fine finish plasters available, or you can mix them by yourself, because clay comes in so many different colors, and that gives you a huge variety of doing different kind of finishes. And of course, different techniques and the tools are possible to achieve endless possibilities. There's on the top left is a work done by Kai Valentine, a great plaster master living in London. He has now actually like imitating the round earth effect with the plaster. Down left is the oven that is finished with very fine clay putty, which is looks like a Venetian plaster, just with the difference that instead of lime, the binder in the mixture is clay. Earthen floors can be done in many different techniques. Plastering is one of them. You can use rend earth, the poured earth, adobe blocks, cob. There's many differences how to build an earthen floor. Of course, if you do the floor, since it needs to be cleaned, and it should be, and it's in direct contact with, it have to be stronger than the regular clay, so I have to treat it. So there are different kind of possibilities how to do it. One of the many common ways is to treat it with the drying oils, which are like linseed oil, boiled linseed oil, tung oil, hemp oil. So oils that are not just drying out, but there's an oxidation process, and they are creating a biopolymer. That's the same reason why linseed oil, for example, for a long time has been traditional also to use to protect timber or the cladding outside. So it's a similar way. You treat the floor with linseed oil, for example, and wax. So it turns into the biopolymer and creates this strong surface that is cleanable and can hold the water as well. And if people maybe often associate the clay plaster with something very rough or something that is just suitable for a countryside or farmhouses, then it's not that. The modern earth finishes are very can be very luxurious and very fine, even shiny if needed. So there's endless possibilities to finish with clay. And of course, if you want to give even more personality to your walls, you can add different kind of natural additives as different kind of organic fibers like straw or flax or crushed seashells or colored marble, whatever, everything that it's and that's possible to treat the walls in a way that you sponge them and you wash them out, so you can see that difference. And different kind of decorative techniques like modeling or sgraffito, stenciling. Stenciling is and lace pattern. You can push it into the wet plaster or plaster through the lace to create patterns on the wall. Or when you use clay paints or other natural paints, you can use also pattern rolls to give some extra patterns on your walls. And decorative elements, of course, using decorative materials. In this case, hempcrete has been used to create the forms. The mixture is of lime and hemp, and then they have been finished with lime or clay plasters. And also the wall panels made of lime plaster or clay plaster to use as painting on the walls. So bio-based materials. As I said before, there's so many other fibers we can use, and we can use them pretty much in a raw way. For example, like straw, reed, hemp as a bales or as a blown-in insulation material. You can also do different kind of products out of them, like fiber boards or these soft insulation materials that are common. And you can use these fibers in the mixtures. As I said, like a hempcrete mixture or light earth, or also in the plasters, in the bricks. There's a lot of possibilities. And so on this slide, there's on top of left there is a gateway building in University Gateway building in England. In the middle top there's a school in France. On the left top, right top, sorry, new real estate development apartment buildings in Switzerland. Down left is a performance art center in France, and down right is a 7-story passive house certified apartment building. What is common in these buildings? Can someone guess?
Natural materials.
These are all insulated with straw. So it's not just a self-builders area or just a residential building area. There are a lot of public buildings in Europe and other countries also that are insulated with straw. In this case, it's mainly like prefab panels were used, but these prefab panels were made project-based. Like for example, this new real estate apartment building in Switzerland, close to this building site, they created a special factory for this real estate production and produced panels. This 7-story apartment building, they have been combined CLT with prefab panels, straw panels, and but there are also many companies that are producing prefab panels. The leading or the pioneer probably on this field is Ecological, company established in Lithuania, now with the headquarters in Slovakia. And in this case, the straw panel itself is like a double timber frame system panel filled with straw with a thickness of 400 millimeters. And often people are thinking that straw is super flammable material. I mean, if you just take one straw, yeah, you can burn it easily. But then this panel, it has been compressed. It's 100 to 120 kilograms per cubic meter, which is just with the right lightness, so we have a really good insulation properties, but it doesn't burn, it just jars. So just the pure panel itself actually stands, has a fire resistance of 30 minutes, which is already enough, mainly in residential buildings, but we would never use it in this way. It's always covered. So in this case, the airtightness is achieved in a different way. So the wall system from inside to outside starts with a decorative clay plaster or some other finish from inside. Then there's a base coat clay plaster, which is reinforced usually, either with jute mesh or some other natural mesh or glass fiber mesh. So the plaster system thickness is 3 centimeters, plastered directly on the straw. And outside from the panel is a membrane. It's that ensures airtightness for this building. So if usually it is done with the vapor barrier from inside, so in this case it's done from outside. Because clay plaster can handle the humidity very well from inside, it's the proper thickness, and clay can balance the relative humidity in the rooms by absorbing the moisture and giving it back in the room but also it's vapor diffusion in open construction, so the moisture can go outside from the construction, but can't come inside because of the membrane that is on top of the panel. And also that membrane ensures that during the construction you can really quickly protect the panels from the weather. On top of the membrane there is another product from the company Jüri was representing in the morning. It's a Styco wood fiber board, 6 centimeters. It's a plasterable wood fiber board, and you can choose then either you want to use a cladding on the facade or a plaster. And the system, without the facade finishing, without cladding, without plaster, just the wood fiber board, the membrane, the panel, and the clay plaster system gives you fire resistance of 120 minutes. This system is also a passive house element, certified component by the Passive House Institute in Germany, and with the cradle-to-cradle silver certified. So this is a newly built factory in Slovakia. There's one production in Lithuania, the new one is now in Slovakia. It starts to fully operating in September. It's fully automated and also built with Ecological panels, combining them with the LVL truss system. And yeah, in the future, everything will be automated, robotics producing the panel. Currently in construction in Sweden is a 10-story building using Ecological straw panels and massed timber trusses. The construction has started this year with the foundation, and at the moment they probably already are installing the timber part. Another high-rise building just got the green light in Netherlands. It's a 13-story tower building. Will be built also combining mass timber, concrete, and it will be insulated with Ecological straw panels. And this is a 155 square meter logistics center in Netherlands, designed by Danish architectural bureau Henning Larsen. Currently Europe's largest timber logistics center, and will be also built with using Ecological straw panels and timber and some other bio-based materials. Plus the whole roof of the building is a green roof, and also there's an artificial wetland surrounding the building, so they try to improve the biodiversity in the area. So this is a quick overview of some of the roads that modern ecological building is moving at the moment. Although the materials are something that people have been using so long time, our work is also like to modernize them daily basis so they would be adaptable for nowadays needs and wishes. But also since the ecological footprint of the material is a really hot subject at the moment and continue to do so we have to develop and adapt them and introduce them and also convince people that this is the way to go, and there's nothing to afraid, because if you look around us, then all the buildings that have been standing around us thousands of years, hundreds of years, actually have been built with natural materials. So, thank you.